A warm greetings to one and all. I'm Sai Padmeshwari from CSC AIML B section. Today we are going to discuss a topic about effect of doping in the active region of 630 nm band land algan textiles trained quantum well lasers. Here, I gave the content that we are going to discuss in this topic: introduction, calculation method, result and discussion, conclusion. Introduction. Recently, there have been extensive studies on store wavelength, GAN, ALGAN stained quantum well lasers for their application to optical data storage, laser printers, barcode readers, etc. The threshold current of such lasers is typically high due to the inheritance limitation of the laser material system. This problem is serious, ex- especially for lasers extending at the 360 nm band. The threshold current can be reduced by introducing tensile or compressive strain to QWs. However, the reduction of the threshold current is limited because the leakage current, which plays an important part of the threshold current, cannot be surpassed expensively. A great reduction of the threshold current has been demonstrated by N-type dropping in the active region of lasers in gas, L-gas, and in L-GAN's INP systems. In addition, the N-type doped lasers has a shorter emission wavelength compared with that of undoped lasers. A short emission wavelength is described for application in optical data storage. The mechanism of the threshold current in 360 nm GLAN LGAN lasers is more competitive than that of these lasers, which have a negligible leakage current. Introduction doping of the active region of lamp algan lasers may affect not only the radiative current and the emission wavelength, but also the leakage current. In this paper, the effect of doping in the active region of 630 nm band GLAN algan lasers are investigated theoretically. The calculation method is described briefly in section 2. The result indicated that both the threshold current and the emission wavelength can be improved by introducing n-type doping in the active region of multi-quantum well lasers. However, there is no advantage of reducing the threshold current by introducing n-type doping for single quantum well lasers. Calculation method. The major part of the calculation method used in the paper has been described in detail in our previous work. We considered lasers with a convolutional step index, separate confinement hetero, heterostructure shown in figure 1 is the illusion for the band profile around the active region of the laser at third stone. The band profile is assumed to be nearly flat in the situation. There are two types of stages taken into account in calculation. One is the bound state confined to the QWs. The other is the continuum states lying in the subbands with energy higher than the barriers. The subbands are contains because one side of the condition and the valence band profiles is open. In practical calculation, the containment states are described by imposing a fictitious calculation method. The major part of the calculation method used in this paper has been described in detail in the previous work. We consider lasers with a conventional step index, separate confinement heterostructure shown in 1 is the illusion for the band profile around the active region of the lasers of the the band profile is assumed to be nearly flat in the situation. There are two types of states taken into account in the calculation. One is the bound state confined to the QWs. The other is the containment states lying in the subbands with the energy higher than the barriers. The bands are containment because one side of the condition and the variance band profiles is open. In practical calculation, the containment states are described by imposing a featureless infinite potential barriers far away from the active region on the one side. We consider the distribution of carriers in the two types of states and the transition between these states. The total optical transition is therefore composed of four components. One, the bond to bond. Second, bond to continue. The continue to bond. The continue to continuous transitions. The continuous states are generally neglected in theoretical analysis of QW lasers. It has, however, been demonstrated that for 630 nm band lamp L-lamp lasers, a large amount of carriers may spill out the barriers from the well and hence the optical transitions involving the continuous statements are of considerable importance. The results in a significant contribution to the optical gain and the radioactive recombination current. The bound various states are obtained by using the Luttinger cons Hamilton, which consists the deformant potentials to consider the strain effect. The inclusion of the coupling of the slit or orbital split of bands to the Hamilton is necessary for such short wavelength lasers since the split of energy of the wide bandgap material is small. In calculating the containment states, we do not consider the band mixing and assume that the active region is bound with two infinite potential barriers separated further enough way. We obtain the bond condition states and the continuous statements by solving the one band effective mass equation. Once the wave function or their energies are solved, the momentum matrix, matrix elements, all components of the gain and those of the spontaneous emission rate can be obtained using the formula in. This is what fancy that the line shape bonding resulting for the carrier intraday relaxation is important in determining the gain spectrum. A simple Lagrangian line shape function is usually used in the gain calculation. It is, however, improper for gain calculation in the work. The slow line shape trail of the Lorentz line shape on the low energy side gives rise to an irresponsibly large absorption of photon with energy well below the band gap, inconsistent with the observed result. In this study, the choice of the line shape function is especially important since the continuous statements are included in the calculation. A poorly chosen line shape with res- result in a large absorption loss due to the optical transition between the continuous states. The actual line shape function should be derived by considering the non-Markovian relaxation process in the QW. However, driving the non-Markovian line shape for the first principle will greatly increase the completion and the computation time in the device stimulation. It is found that the non-Malvern line shape can be well filtered by the simple figure 2. The non-Machiavellian line shape function with c is equals to 0.005 EV, K is equals to 10 EV1 and K2 is equals to 30 EV1 and the Lorentzian line shape function with a zero point 0.1 minus PS relaxation lifetime. Result and discussion. In this section, we are show and discuss the calculation result for the SCH lasers. The laser structures are composed of 8 nm GA in P, tensile stained QW, ALGA in P various layers, 200 nm in P confining layers and 2 1M algan cladding layers. The dopant concentration in the P cladding layer is assumed to be 1 or 10 centimeters and that in the encladding layers is high sufficiently so that the whole leakage current can be neglected. The creative length of the lasers is given to be 500 and the internal loss is assumed to be 100 centimeters. The temperature is 30 K. Figure 3 shows the calculation result and percent hole as function of the dopant concentration in the active region for lasers, laser structures with the three quantum wells and three different contents of the barriers are considered zero point 0.4, 0.5 and zero point 0.6 shown in the calculation result of the radiation combination current density as can be seen decreased with the increase in donor concentration but increase with the increase in acceptor concentration. Here, the bar graphs of the four concentrations. Conclusion. We have theoretically analyzed 330 nm band length and argon tensile stained QW lasers with a doped active region. The results shown that the Thurston hole current can be reduced and the emission wavelength can be shortened by the introducing n-type doping to multi-quantum well lasers. But for SQW lasers, the Threshold current increases with the n-type doping because of the laser increase in the liquid current. Thank you.